In this video, we'll talk about how do we get to the estimates of these population parameters that we were talking about. So how do we estimate beta naught and beta 1? Okay. So let's think about our data. Think about our data as we have some data on x and y, and xi represents the ith unit, because this is a cross-sectional data set. Yi represents the value for y for the ith unit, right? So we have some data where I goes from 1 to n, and this is n is our sample size, right? So we remember we had a population and we extract a sample from it, a random sample. So the next graph is going to show you some sample, which is like a really small sample of 15 families. So n is 15. And on the x-axis, we have income, and we're trying to explain saving behavior with income. And you can see sort of that with the scatter plot, you have some outliers here, right? At high levels of income, you have high levels of saving, right? These points right here. And at low levels of income, you have low levels of saving, right? This is almost zero here, right? So what we want to do is always to get to the slope, right? We want to fit this line through our data. We want to fit this regression line through our data. We want to get to the we want to basically rotate this line and figure out, well, where is this distance? This is the distance between the line is our prediction, right? This is the predicted value. This is predicted and this is actual, right? And we have those points, right? There's this distance. This is actual value. This is the distance between the line and those data points that we have, right? Some are below the line, some are above the line, right? What we want to do is we want to minimize the squared residuals, right? We'll see this later. How do we minimize the squared residuals? But residuals here is basically this distance between the regression line, right, that we are trying to fit in this data, through this data, and the actual value, the actual values, okay? So that's what we want to run with, okay? Now, there are different ways of getting to the OLS estimates, okay? So the first way is we could use the two restrictions that we talked about earlier, one being that the expected value of U is equal to 0, right? The average amount of ability or land quality or anything else that we had put in U is equal to 0. And we said that, well, that is a harmless assumption because it only changes the intercept. The second assumption was that the x and u are uncorrelated, right? So it was a simplifying assumption. But both of these assumptions are implied from this assumption that says the expected value of u given x is 0, right? So if we combine these, then somehow we get to that. Okay, so now, given those assumptions, the expected value of u is equal to 0 and the covariance, right? If we said correlation between x and u is 0, then the covariance is 0. That's given, right? Is the same as saying that the expected value of x u is equal to 0, right? So recall from your statistics courses that the covariance between any two variables is given by this formula, right? Using the expectations operator. So the covariance between x and u is equal to the expected value of xu minus the expected value of x times the expected value of u. So if we know that the expected value of u is equal to 0, this term cancels and we are left with the expected value of xu, right? And this is the covariance. So in other words, we can say if we are assuming that x and u are uncorrelated, then the covariance will also be 0. So this holds. Okay, and here we can write out what u is, right? So if we remember, we said that the linear regression model is beta naught y equals beta naught plus beta 1 x plus u, and you can then say, well, this implies u equals y minus beta naught minus beta 1 x, right? So if we plug in this right here into the expected value of u, we get this first equation, okay? And if we try to use this equation, right, which is the second equation, we can then plug in what u is into our second equation and get two equations, right? So we have beta naught and beta 1 that we want to estimate. We have two equations in two unknowns, right? So these are the unknowns. We want to estimate this, and we have the data on y and x, right? So two equations and two unknowns, okay? So we can use this, okay? So you can use some calculus and you're going to find that we can basically convert we can go between the expectations operator and the summations operator, right? So we can always go, if you want to, you can refresh your memory here, but basically we are going between the expectations operator to saying that we can write the expectations operator also as 1 over n, right? And summate it over all the values of y and x, right? Or whatever we have here of u, for example. So the expected value of u equals 0 can also be written as this, right? Where this guy right here is just u, okay? And u hat because we are trying to estimate these, right? We're trying to get at the estimates. So whenever you see hat written on beta 1 or beta naught or beta 1, we're basically talking about estimates using data. Okay, similarly, the second condition can be written in this way. Okay, and so we can use some algebra and we can get to the first equation. The first equation, if you solve this, you're going to get to this, and you're going to set that equal to 0. Okay, and then you're going to basically say that the mean or the average of y and x basically lies on that regression line that we saw. Okay, so x bar and y bar are points that lie on the line, on the regression line that we fit. Okay, so these are sample averages or means. Okay, so we can do a little bit of more algebra and get to basically this slope parameter slope estimate that we were interested in, which is in terms of x and y. Okay, so here we can see that we have this equation, right? And there's only this one unknown. Okay. Now, there are different ways of using the formula for beta 1 hat to get to different algebraic expressions, okay? So the first one is easy to prove. The second one might take you a little bit longer, but all of these are equivalent expressions, okay? And this helps us basically work through the proof sometimes when we're thinking about writing down the expression for beta 1 hat, okay? So what we get to in the end is an expression for beta 1 hat, which basically says that beta 1 hat is a ratio. And it's a ratio of the sample covariance between x and y divided by the sample variance of x, okay? This is really important to note that what do you have in the denominator here? In the denominator, we must have some variation in x. We must have variation in x. Okay, and in the numerator, we have the covariance between x and y. Now, the formula that I showed you is important because it tells us that we can take the data that we have and we can compute the slope estimate, okay? And we can only compute the slope estimate if the variance, which is variance of x, where we're talking about variance of x, in the denominator is not equal to 0, okay? So I'm going to show you an example where we may not be able to estimate beta 1 hat, which is the slope. We may not be able to. You cannot do that, okay? So let's see in what case can we not, okay, estimate this. So notice here we have education on the x-axis, we have wages on the y-axis, and for 12 years of education, for x equals 12, there is no variation in y. Okay, so you see all of these different points, if we were to write down the coordinates, you're going to find that it's always going to be 12 years of education and some value of y. Then here also, this is 12 years of education and some value of y, right? This is x comma y, right? And you're seeing that there is absolutely no variation in x, right? I'm sorry, here this should be x. There is no variation in x, okay? And so this makes the estimation of beta 1 hat infeasible, okay? So we needed, remember the formula here, we needed some variation in x in our denominator. If x is constant, then the variation is 0. And if you have 0 in the denominator, then you basically have this undefined, right? And that's why you can't calculate it. So it's always good to graph your data because, you know, you want to make sure that you're trying to capture something, right? The idea is to you basically capture changes in y with respect to changes in x. Okay, now we might not encounter such a situation mostly in our data because we might actually have large data sets. This type of a problem actually occurs in small sample sizes where where this can be sometimes difficult to compute, okay? Now, once we've estimated beta 1 hat, we basically can use the fact that y bar and x bar, the means of y and x, lie on the regression line and compute the value for beta naught hat, okay? And that's our intercept. So the nice thing is that because we will use statistical software, we're not trying to calculate this by hand, but we should know the machinery behind this.